We learned about how you can sketch semi-informally of the proof obligation rule of invariant preservation for our model. And if you recall, this is the sequence that we spoke about in detail in the earlier part of the lecture. And make sure you understand the components over here informally. Make sure I understand the illustration I did earlier. And what we want to do now is to really transform every one of them into formal construct that will be applicable to any model that you may derive later. So that it has to be a completely formal and general approach. That's something I would like to do. And so for this part of the lecture, I would like to talk about all the formal components which will correspond to each one of these in the sequence, first of all. That'll be for the purpose for this part. And in the next part, I will actually combine all the components together and give you the ultimate sequence rule. That's actually for the proof obligation for invariant preservation. So that'll be the plan, right? So let's talk about the components first. And the components is going to be very general, very abstract, but I'm going to use our model M0 as an example to illustrate every one of them. It's not too bad, right? But you really want to understand what we really try to do here is to be completely formal and general. Otherwise, things cannot be done systematically for all the system across application domains. All right. What I want to do is I want you to remind you about this summary of the model that we have got so far. We got constant, we got variables, we got axiom, we got invariants, we got the two events over here. Okay, let me now introduce the components one by one. The first one here is called C over here, which will be a list of constant. Let me talk about it and I'll give you example. Okay, right, I got all the components over here which I will show to you in the slides. I'll go over them, but for now I just want to talk about individually one by one. Okay, the first one is C over here. So this is C is simply a list of constant, and notice that I really meant a list over here. In general, you may have more than one constants in your model. Of course, in our initial model, it's simple. We only got one single constant. But the way you want to think about it is we're going to instantiate this general components C over here by a singleton list, meaning that it's only a list containing one single constant. So the example I like to give you is, you can see here, so we got constant D over here. So you can think about, in this particular case, we actually got the C is actually equal to what you can think about is by definition, right? Triangle equal. By definition for this model here, it will be simply a list, right? So that's how we represent a list. What you think about is like an array, but not so recommended. Array is more like a programming concept. Think about it's more like a list. And we only got one single constant in our initial model, so only put D over here. If you actually got more than one constant in your model, which we'll see later, in which case you're going to get a common separated list of constant, right? The first component is pretty straightforward, just a list of constant. All right, let's see what the next one is. Now that we got a constant, of course we got axioms, which will actually be the constraints on the constants, right? So we're going to talk about A of C, so that'll be the axiom. Let's talk about it. And you can see, not surprisingly, I also said here it's going to be a list of axiom, because in general you may have more than one axioms associated with all the multiple constant you might have, but at the moment we only got one, right? If you got multiple constant in the list, of course you will get multiple axiom in the list as well. Okay, so the way we actually talk about it is like this. So we got A of C over here, right? So here we simply say the axiom is going to be more, mathematically speaking, think about axiom is more like a function, and the function is going to be applied to the list, applied to some constant, like the list of constant over here. Okay, so if you think about the axiom we have over here would be, let me write it down. So the axiom of the constant list, by definition, right, for this particular model, what we have is only a single axiom, which will be axiom 0_1, right? Remember we talked about the naming convention. So it's axiom, AXM, initial model 0, and also axiom number 1, but only got one. So there's only a single list. So we can say over here, axiom for initial model 0, and then number 1. That's all we have over here, just a list, right? And In general, you can also refer to some individual axiom. So you can think about it's more like an indexed array, but it's not really array because in the mathematically we may just start the index with 1. So here we can write a index 1 over here, the axiom. So this part here is referring to the entire list of axiom, and this one over here is referring to index 1 into the list, right? So this will be, by definition, for our model, is going to refer to just the axiom itself. Right? Notice the difference over here. Precision is really important. When I refer to the entire axiom list, it's going to be a list. When I refer to the axiom list with a particular indexing over here, it's going to be just a single axiom, right? Hopefully that's clear to you. Right? So that's about the axiom list, which is also a very straightforward idea, but in general, it could be a list, comma-separated list as well. Let's now go back to see the next one. And we talk about constant axiom, it would make sense to talk about variables and also invariants, right? Very similar idea. Let's talk about it. And for the variables, since we have to distinguish between the notions of pre-state and also post-states, so we better be careful, right? Let's now talk about it. Okay. So we have pre and also post. So V here will be the pre-state value, and V prime will be the post-state value, right? So in the pre-states and also the post-states. Let's now talk about it. Okay. So when we have the same variable over here, the same variable n is going to be referred to either in the pre-states or in the post-states, either way. Right? Let's now write down the list. In the pre-states, we simply got V over here, and by definition for our model, it's going to be just a list of single variable, just n. You can see for our initial model, even though it's a list, but there's only a single element in that. But you should really understand, in general, you may have more than one, like a variable or constant or axiom in the list, right? Just in general, when we get to the more complicated refinements later. And the next step will be if I simply got V prime. And by definition, it's going to be the same variable, but I'm talking about its post-state value. So I'm going to prime it over here, right? So you can see this is the pre-states variable list, and this is the post-states variable list. Right? So these are the two separate lists that you should really distinguish. And the next one will be about the invariance. Okay, you can see invariant itself may refer to either the constants and or the variable. So that's why you want to think about invariant is more like a function, which depends on some parts of the constant list or the variable list. So that's why we say it's a list of invariant. Idea will be very similar about how we index the axioms. Let's take a look. Let's take a look at some example. Okay, and for the invariants, let's now switch to maybe blue over here. Okay, for the invariants, let me just a little bit thicker. For the invariant, we got 2 in this case, right? It's definitely a list for sure. Okay, let's talk about it. And for the invariants, what we have is we have invariant I, which may refer to the C or the V, right? And of course, over here for C and V, we know what they are. So you can think about the C over here is simply just the constant D over here, and the V over here is the variable n, right? So this will be the C, this will be the V, right? If you want to, I can also change this slightly over here. Let me just modify this very quickly. So when we talk about the axiom over here, right? Let me just be careful over here. So when I talk about the axiom, before you can see the C over here is simply just the constant, which will be the D list, right? And also this will also be just D over here, right? You can see the list of axiom, and this will be the list of axiom as well, but indexed with 1, right? It makes sense. Right, let's go back to the invariants. How many invariants do we have in this case? We got 2, right? Either this or this. So it's going to be a single list of 2 elements. Invariance of model 0 but index 1. And also the invariance of the same model 0 but index 2, right? And we can definitely use the indexing notation if you want. I can say I1 index 1, and then I'm still using the same constant list and also variable list. In that case, what would that be? That would be just the first one. Invariant for model 0 and 1, right? You can see index 1, we're getting this. Index 2, we're getting this, right? Let me write it down for completeness. Invariant 2, and then the same constant list, the same variable list. That'll be invariant for model 0, but index 2. Right? You can definitely see that index 2 is referring to the second one in the list. All right? Right, so that's about invariant, how we refer to it. Right? So this will be this. Okay, let me just make it a little bit thicker. Invariance. All right, so that's about this particular column over here I want to speak about. It's very basic and also straightforward. We got the list of constant, axiom, variable in the two different states before or after the transition, and also the invariance. Let's talk about the other three, which would be more relevant to individual events. Remember, for every proof obligation, we have to instantiate it for every event, right? So that's why we want to talk about the specific details of each event. Each proof obligation rule should be instantiated for every event. In our case, we got two events over here, right? We got ML out, we got ML in. So later in the next part, you will see that I will instantiate the proof obligation individually for these two events. That's what you will see. But just remember that rule, which I also spoke about earlier, right? Instantiated for every event. That's for each proof obligation rule. All right. Let's now move on to talk about three more. Okay. And we also got the guards of the events. So that will determine whether or not the events will be enabled, right? If guard evaluates the true in the current state, in the pre-state, in that case, you will be enabled, and then the event can be executed for its action. So will result in some post states. And let's now take a look. This one is actually rather simple, because for the guard for the event may refer to some constant, or it may refer to some variable. At the moment, the guard is simply true for ML out and ML in. But let me just talk about a general case. Later on, when we have, if we have to fix the guards for ML in and ML out, we definitely can. You will definitely see it cannot be just true, right? Let's talk about the guard over here. And for the guards, let me now highlight it. The guard over here, the guards of an event. Okay, there's a little bit typo over here. I really meant just events over here. All right. Okay, so we got the special case for our initial model. So we want to talk about the guard. You can see over here is missing for ML out, also missing for ML in. So that means the guard, which may refer to the constant D or the variable N. Right? So that's the guard. In this case, it will be by definition simply just true because it's missing. Similarly, for the case of ML in, we also can figure out its guard, which in general can refer to the constant list, in this case just D, and also the variable list, in this case just N. And in this case, by definition, since it's missing, that's also true. So that's the guard. But later on, if we introduce any actual guard into ML in or ML out, we're going to replace the true by something else, right? Just keep that in mind. Okay, so that'll be the guard. And of course, this part over here, just don't forget, this determines whether or not the events will be enabled. So this really determines the enableness of the events. Determined enableness of the events. Right, so over here, the enableness. That's also the term we spoke about last week, right? All right, we talk about the guard. Let's talk about the actions for the events, right? All right, so that's the examples I just went through. So what about effects? So this E over here, you think about E stands for, G over here stands for guard. E over here stands for the effects, right? All the terms we have seen already last week. For every individual event, we have to know exactly what's their effects. And this particular effect is going to tell you what's going to be the post-state value in terms of the pre-state evaluation. That's also some concept we also spoke about earlier this week, right? The effects of the event's action in terms of, that's just the acronym, right? Just make sure you don't get lost. In terms of what the variable values become, right? Let's now take a look. So you can think about this part over here really is, so this is really to say, so this E and CV, right? This is really about values of variables in the post states, but the way we express that is going to be in terms of the pre-state evaluation. I'll show that to you. In post states, in terms of pre-state expression. All right, so now here you want to be sure you actually see I'm talking about number one, the pre-state pre-state expression, but we are really trying to express what the post-state value will become. That's what we're doing, right? Let's take a look. Let's talk about, let's say, for ML out. For ML out over here, what would be its effects? Okay, you can first of all think about what the before-after predicate is. The before-after predicate, as we spoke about before, this one will be the before-after predicate is simply m prime is equal to m plus 1, meaning that the post-state value in terms of the pre-state evaluation will be m plus 1. Okay, and also similarly, I'm also going to talk about ML in as well, right? That's also, to really know it, we also need to know its before-after predicate, which we know already. Before-after predicate, m prime is equal to n minus 1. All right, let's now talk about this particular E components. So the E over here, in general, it may refer to the constant D, or it may refer to the variable n. And in the case of ML out, what is that? That's basically just about, since we got the variable n over here is a list, so the effect is also going to be a list because a single event action may try to modify multiple variables. So that's why you're going to enumerate all the updates. In this case, there's only one single action. So in the list, we only contain just one action, just one effects. So that will be just n plus 1. Right? You can see the n plus 1 is really corresponding to what we are having over here, right? So this is the pre-state evaluation to specify what the post-state value should really become for variable n. If you got more than one updates, if you got updates for more than one variables, this list should be extended by maybe to maybe 2 or 3, right? But in this case, there's only one action, so that's why there's only one effects in the list. Similarly, if we talk about MLN over here, the effects for that, again, you may refer to the constant, you may refer to the variable over here. By definition, over here, what about the pre-state evaluation for the post-state in this case? Well, you can see it's different effects, right? If I take the transition for MLN, in that case, the effects will be the post-state value is going to become the pre-state value minus 1, right? It's different. So there's going to be a list, which will be n minus 1. So you can definitely see that. So these two expressions, n plus 1 versus n minus 1, they're different. All right? And there should be a list because in general, you may actually try to perform more than one actions to modify more than one variables. So that's why it should be a list. All right? In general. So that's about the effects. And the final components that we should look at is more like a additional on the relevant notes. We want to know what about the before-after predicate that we spoke about before. The before-after predicate usually will just be an equality between to specify the relation between the post-state value that's primed and also pre-state value, right? You can see here the v prime over here is referring to the list of variable that's primed, refer to their values in the post states. And how do we specify the before-after predicate over here? So let me just say, this is just an aside. If you look at this particular before-after predicate over here, if you look at that, and also the before-after predicate over here, and we are basically talking about this, the before-after predicate, right? Okay. In this case, let me put it down over here. The before-after predicate, simply think about, it's more like the list of variable in the post states will simply just be n prime, right? you can see the n prime is what we said earlier over here, right? We're saying that this will be simply substituted by some pre-state value, which pre-state evaluation, which will be in this case just n plus 1, right? You can see it's by definition E of CV. So that would just be n plus 1. It looks a little bit hilarious over here. Why are you putting brackets around over here? It's because in general, the actions for each event may involve the changes on both multiple variables, maybe more than one. In this case, of course, we only got n prime is equal to n plus 1. But later on, if we got multiple variables, in that case, we may want to say another variable over here, and also its corresponding pre-state evaluation for its post-state value. Okay? And let's now, for completeness, what about this part over here? So for this part over here, this expression over here for the before after predicate would be, we also got the list of prime variable for the post states. It should be equal to, right? In this case, you can see the effects is actually over here, n minus 1, right? It's going to be n minus 1. So this part over here and this part over here really correspond to the before after predicate that we spoke about last time. That's really consistent, right? Nothing is inconsistent. Alrighty, let's now go back to the slide, and that's about everything you should really know about the formal components over here. And make sure you understand about each formal component over here, and then in the next part, we will actually try to combine all these into formulating a sequence that will represent the proof obligation of invariant preservation.